Hello students, welcome back. Now let's finally take care of some theoretical details of Fullman's method. We went through example problems already. All that's left is some theoretical detail. Basically we want this, but without calculating the inverse matrix. That's the idea. So how do we do that? Let's come back here. This matrix is called the resolvent matrix, and the determinant of Si minus A is called the characteristic polynomial. And the existence of inverse matrix is equivalent to the determinant being non-zero. So the existence of resolvent matrix, and consequently the matrix exponential, is equivalent to the characteristic polynomial hitting non-zero, or yes, Q of S is not zero. So S is not a zero of the characteristic polynomial. That probably is the better way to say the same thing. And what if this is equal to zero? And that's what we call eigenvalues, or characteristic values. And just like the one-dimensional, the usual case, we have 1 over S minus A, then denominator hits zero. And that was a special case. And likewise here, if this determinant of Si minus A is equal to 0, that means this inverse matrix does not exist. So this matrix inversion will not make sense. This is a starting point, basically. This is coming from Cramer's inverse matrix formula, and I don't know whether everybody remembers this or not, because I covered it in lesson 13b, the non-essential part. It's here. Cramer's inverse matrix formula goes like this. The denominator is determinant of A, so if the determinant is 0, then the inverse does not exist, and that's clear from this inverse matrix formula. Also, that condition turns out to be necessary and sufficient. Now, -1 plus I plus j, that's because we want the alternating sign, but what's this? Determinant of capital Aij, what is this? This is actually the determinant of the deleted matrix. What is deleted matrix? Let me show you one. For example, if you have this kind of matrix and we have a certain entry, and for example, if I selected this 4, 3, and 3, then I'll just remove everything in the same row and same column. So if I selected 4, 3, and 3, then remove entire row 4 and remove entire column 3. So I removed one row and one column. So this n by n square matrix dropped down to n minus 1 by n minus 1 square matrix. So determinant of that deleted matrix, the n by 1 minus n minus 1, that matrix goes to the numerator. Now let's come back to this. Determinant of Si minus A, and let's see, determinant of Si minus A, Si minus A looks like this. Let me see. Let's put matrix in there. Okay. So S, all those dot, dot, dot. Okay, this is Si minus A is gonna be, well, anything as a matter of fact. It can be anything here. Any wildcard will come here. There's no pattern anywhere. So if I take the determinant, I have to subtract this. So basically I have S, no, let me copy and paste and take one more step. Subtracting, so S minus that, and all those are going to be S minus. You're going to get this kind of pattern here. And all these, well, 0 minus something, so they can be anything. So I don't have any control over any of those. Now, if I take the determinant of all these, how does it work? Select this one and then take the deleted matrix and then take determinant of all this and many more, and take this and then rest and so on and so forth. So at least there should be a multiplication toward this principal diagonal. So we have to have s to the nth power and whatever dot dot dot. And that's going to be the structure of this determinant. Because you have to have this principal diagonal or multiplied. So we have to s to the nth power, and that should be monic. Coefficient is all 1, so we have to have s to the nth power, and then the rest, of course, is going to be complicated. So that is the denominator here. And the numerator will be similar, except that this one is going to go over to, at most, n minus first degree. Because we are dealing with deleted matrix, so we've removed one row, one column. So this one is n minus first degree, and this one is nth degree. And then there may be some additions or something in the numerator, so some simplification. But, you know, in any case, this cannot go up. This is degree n. This one is n minus first degree or lower. So everything is proper rational. So this whole thing, this is proper rational. So this matrix expression here will have this kind of thing. So let's see. Here's a wildcard, numerator, I don't care what that is. And denominator, there will be appropriate factorization. Let's say, let's take k, and then there you go. Whatever polynomial, it can be factored completely all the way down to linear factors if you go to complex number field. That's called the fundamental theorem of algebra. And the multiplicities here will have to add up the degree of the polynomial. So the sum of those multiplicities, m1 plus dot 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 mk, we have to add up to n. And then this numerator has degree less than n, so this is proper. So if you take the decomposition by partial fraction, then you're going to get a bunch of fractions that looks like some coefficient over s minus lambda something. So what happens here has to be of this form. Some kind of summation of some numerator over s minus and some power. of this kind of form. And there are a bunch of them. Now, that's going to be the decomposition by partial fraction. And then if I take the Laplace inversion of this, what do you think you're going to get? You're going to get exponential of, so this one will give me, where's the character here? Special character, Laplace inversion of this thing. So what you're gonna get? Numerator, I don't care, and that's gonna be something complicated. So we're gonna get some coefficient, and then e to the of this form. Let me remove this index. And then we have this multiplicity here, so t to the sum of this kind of form. And then I have a bunch of those, so I'm going to get a summation of all those bunches. And then this is for each entry of the matrix, because we are taking Laplace inversion of each entry, basically. So we're going to get this kind of matrix expression, basically. So that is the matrix exponential. Now, if I decompose all those summation, then you're going to get all those coefficient parts will form each entry, and this one is common, so I can take it outside as a scalar multiplication. So what we have here, we're going to get appropriate matrix here. So we have a coefficient matrix times eigenfunction of that form and bunch of those things added together. So basically we have M1, M2, M3, M4, all those matrices, and then standard bases that look like this. And those are coming from the characteristic polynomial. And then you can set up appropriate system of linear equations to find out those constant matrices, M1, M2, M3, M4. Typical technique we already went through. Plug in t equal to 0, take the derivative and plug in t equal to 0, second derivative and plug in t equal to 0 until you run out of everything. Total n, you'll have to take the derivative n minus 1 times so that you get n equations and n unknowns. So that's the idea. I can use some fancy terms like this in a little bit more precise form with all those indices. If you prefer something like this, that's fine. This is actually a little bit more precise version of these. And then the basis function will have to look like these, because we have these kind of fractions if we take the decomposition by partial fraction. So basis function will be like this. These are the eigenfunctions. And then we have m1 times this, m2 times this, m3 times this. I mean by the capital M1, never mind, let me show you. Kind of like this form. Capital M1, that's coefficient matrix, capital M2, coefficient matrix, dot, 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 capital Mn, coefficient matrix, like this. And then all these are the basis functions here. And by n, so we have to have those n bases. In the previous example, we went through, for example, in the second example here, we had 3 basis functions, and those were e to the t power, and e to the t cosine of t, and also e to the t sine of t, and e to the t power came from this factor here, and the eigenvalue was 1. And the other two came from this quadratic irreducible part, where the eigenvalue is 1 plus I and 1 minus I, respectively. In this case, just 2 by 2, and yes, it looks like this. We have s minus 4 squared, so e to the 4t, and then t times e to the 4t, we got those two. So first coefficient matrix like this, and then second coefficient matrix like those. In any case, the most general form is kind of like these. So yes, everything works out, and then theoretically perfect. So you can use this Fulmer's method. Now, how practical this is, I'm not exactly sure because this too is highly computation intensive. Nonetheless, we'll have to use some of those to answer some problems in section 4, and that's what we are up to. Let's stop here.